Welcome to Unit 4, Lesson 15. We are writing systems of equations. Today what we're going to do is write some systems of equations from real-world situations, but we're also still going to be doing a little bit of solving some solutions or some systems. Something that really helps out as a strategy for being able to solve a system of equations is having an idea of how many solutions it's going to have before I even get started. The way that we can do that is we need to understand what these solutions look like. So when we talk about no solutions, we talk about having a set of parallel lines. When we talk about parallel lines, we understand that we have equal slopes, but we have different y-intercepts. So the y-intercepts can't be the same, obviously, or else they would be passing through the same point. So the concept is we want parallel lines that are equal slopes, but different y-intercepts, so we see two lines that can never intersect. One solution is obviously two lines that intersect at one single point. Intersecting lines only happens based on one thing, and that's different slopes. So if you're looking at two equations and you see that the slopes are different, or you can conclude that the slopes are different, then you can also conclude that there is one solution that's actually going to be present. Finally, infinitely many solutions, what we see is quote unquote one line. The reason for this is because the two lines overlap directly on each other, and they overlap because they have equal slopes and they have equal y-intercepts. Another thing that could potentially happen here is that you have all of the variable terms. So when we're talking about in standard form, which means a times x plus b times y is equal to c. A is equal to A and B is equal to B. C is not, and C is equal to C. Okay, in no solution, we would see A is equal to A, B is equal to B, C is not equal to C. That's not to say that C is the y-intercept, but it is a part of it. So notice the difference in standard form. When A, B, and C, the coefficients of x and y and the constant at the end are equal, we have infinitely many solutions. But when the coefficients of x and y are equal and the constant is not equal, then we have no solution. So let's take this information right here and let's classify these. The very first set right here, y is equal to negative 3/4 of x plus 4, and y is equal to negative 4/3 of x plus minus 1. What we see right here is we see the slopes as the coefficient of x are equal. So we know right now that this is not one solution because the slopes are equal. But we see that they intersect the y-axis at different points. This one would have to be, number one, no solution. Simply because we see that the lines are parallel, they have the same slope, but they don't pass through the same point. Number B, or letter B, we have two lines with a slope of 4 and one with a slope of negative 2. Immediately, I see different slopes, and so I know that this one is one solution. We could find that solution. We're not going to at this time. Letter C looks a little bit deceiving. Right now, we see that A and B and C are not equal to each other at all. But we also can see something else if we look a little closer. We look at 2x and 4x, and then we look at 3y and 6y. What we'll notice with this is that the second equation, at least in the A and the B, is twice the value of the first equation. And so what we can conclude from that is that this second equation, if I used a common factor of 2 and divided all the way across, I could get 2 times x plus 6 times y is equal to, 3 times y. So half of that one is equal to half of 17, which is 8 5/10. And then what I recognize with this is comparing it to the other equation is they look almost exactly the same, but not quite. I see that the A terms are equal in the 2. The B terms are equal, but the C terms are not. This tells me that I have no solution. The slopes of these two lines will be equal, but the y-intercepts will not. And finally, this last one, letter D, I really should simplify this to find out 5 times x minus 15. And then what I really see is that these two equations are exactly the same equation. I have infinitely many solutions. All right. The next set of work we're going to do is situations and systems. For each situation, we have two tasks. Number one, we need to create a system of equations, meaning we have to write two equations that are going to go with this. And then the second thing we have to do is interpret those two equations and basically say, we're not being asked to solve them. We're being asked to say, what is the purpose for this system? So without solving, we would interpret what the solution to the system would tell you about the situation, not that we actually have to solve it. So the first one we're looking at, something that I would always recommend as we do this, is that we make sure that we identify our variables and we define our variables before we get going into anything else. So when we talk about these variables, we want to look at what it says and look at what we don't know. And there's, in a system of equations, there's always going to be two. So in this case, Lynn's family's out for a bike ride. When her dad stops to take a picture of the scenery, he tells the family to keep going, the rest of the family to keep going, and they'll catch up. So Lynn's dad spends 5 minutes taking the photo and then rides at 2,400 miles per minute until he meets up with the rest of the family that's further along the bike path. Lynn and the rest of the family were riding at 1,800 miles per minute. So considering with these pieces, there's a couple of things. We know that there's time, and this time is in minutes. And then we know that there's some distances that are happening. One of the cool things that we can look at if we're never not sure is we can look for phrases like this, miles per minute. Okay, and again, right here, miles per minute. And what that helps me to understand is that our time is going to equal time in minutes. And then D, we'll let that be distance in miles. Now what happens with this is now I can write two different equations. We have two different scenarios here. We have dad who has stopped and waited, and then we have the rest of the family that's continued on. But we have to consider something about these two situations. First off, dad spent 5 minutes waiting. That gave the rest of the family 5 extra minutes to work. So let's talk about the family first, and then let's talk about dad. So in the family, we know that their distance is going to be equal to a constant rate of 1,800 miles per minute. So if I think about just that factor, oh my goodness, not xt. If I think about just that factor, that would be assuming that there is nothing different. They just kept going at a constant rate. When we have to look at this in a different situation, we have to account for that 5 minutes of extra time that they did, but that 5 minutes of extra time is isolated strictly to the time, which means that after that 5 minutes, they've gotten a certain distance away while dad was waiting to take a picture. So what we need to consider with this is how far were they before dad started riding again? To do that, we're going to take and do the distributive property, and we'll recognize that the family is traveling indeed at a rate of 1,800 miles per second. But how far were they ahead when dad finally got going again? They were, after 5 minutes, 4.5 miles. Let me double check. That doesn't quite seem right. 1,800 times 5. There we go. They were 9/10 of a mile down the path when dad started to ride again. And so now what we need to do is we need to talk about dad's path, and dad's is a little bit easier because dad is actually traveling at a rate of 2,400 miles per second. And so what we do is with our simplified version of this, we find out that our system of equations is these two equations, the simplified form of the family compared to dad. And then what will this find out? Well, what this is going to do for us, the solution tells us how long it would take Lynn's dad to catch up. How much time dad takes to catch up. And the reason I know that is this. Both equations are equal to the same thing. So the distance would be equal at what time? And with just for your bonus piece, what would that mean? It would mean that the family has traveled 1800ths of a minute or 1800 miles per minute plus the 900 miles that they've already gone. And that would have to equal to the 2400ths miles per minute that dad is traveling on his bike. And at what point they would equal, that would tell us that the time is equal and the distance we already know is equal at that time. So that's what that one does. Number 2, we have Noah is planning a kayaking trip. Kayak rental A charges a base fee of $15 plus $4.50 per hour. Kayak rental B charges a base fee of $12.50 plus $5 per hour. This one's kind of cool because we can see a couple things right away. First off, I think it's pretty easy that we're talking about time in hours. So let's let X be time in hours. And then we can go ahead and say let Y be the total rental fee. Okay. And then at this point, I think it's pretty easy. Rental company A is going to have a fee of Y equals the total fee is $15 plus $4.50 per hour. And then rental company B would be Y is equal to $12.50. I'll go ahead and put the 0 in here just to make it a little bit more usable, plus $5 per hour. And then we need to have this brace on here to be able to prove that these two are related, or to show that these are two are related and grouped together. And what would the answer be if we were to go ahead and compare the two of these together? Consider the part that the total costs are going to be equal together and that the time is going to have to be an equal value. And so we would have to say the solution represents, or solution shows, the cost of each rental company at the same time. Now, why would I use something like this? Well, the reality is if I plan on being gone for a long time during the day, one of these companies is going to be cheaper. If I'm planning to be gone for like 16, 20 hours, I have to consider which company is going to charge me more at that point. And I can use this to determine which one of these equations or which one of these companies is actually going to be cheaper for me. If I'm talking about a short term, then one company will be less. One of the ways that I can determine that is simply by taking the value and saying, if I'm out for 1 hour, company A is going to cost me $19.50 and company B is going to cost me $17.50. But what about 2 hours and 3 hours and 4 hours? At what point do these companies show or charge the exact same amount? How long would that be and how much would it be? And then what point would I need to consider using a different company? Because at some point, company B is going to become more expensive. So a short term, I would tell you that company A is probably not your choice, is not your best choice, but at some point, company B will not be the right choice either. And we would simply do that by setting this expression, or the first equation, 15 plus 450x is equal to 1250 plus 5x. And when I find out that x, I find out exactly how much time the two companies, or how long I can have the kayak for the exact same cost. And then I determine which company is better. So this company is better for short term. This company is better for long term. Number 3, Diego's making a large batch of pastries. The recipe calls for 3 strawberries for every apple. Diego must use 52 fruits altogether. So what we're looking for is, on this one's just a little bit different. He's making a large batch of pastries. The recipe calls for 3 strawberries for every apple. So how would I actually write that piece? Well, let's see here. He's probably going to need something that talks about the number of apples. So we can call that the number of apples A. So we'll say let A be number of apples, and let S be number of strawberries. Okay. And with that in mind, what I have to consider with that is, what would I do if I needed to write these out? How would I consider this? Well, here's the first equation. is he has, it's 3 strawberries are going to be equal to every apple. So we can say that 3s is equal to A. But then we also have to have this other piece where we talk about that he has to have 52 fruits altogether. So when he takes his strawberries, 3 strawberries, or excuse me, the number of strawberries plus the number of apples, it has to equal 52. And so with these two systems, what we find out is that 3 strawberries is equal to 1 apple, but then he has all these apples plus all the strawberries that have to be equal to 52 total fruits. And what would this tell me at the end? Well, the solution is going to tell me how much of each fruit I need to use. Okay, talking about really a large batch. So the last one, number 4, the cost of flour is 80 cents per pound. And then sugar costs 50 cents per pound. An order of flour and sugar weighs 15 pounds and costs $9. So again, we're looking at a couple things. So maybe we can say let F be pounds of flour and let S be pounds of sugar. And now we have 2 equations. We're looking for 2 things. We need to know how many pounds we're actually working with and how many costs, or what our total cost is. So we know that our total pounds is 15. We know that our total cost is 9. So how would I figure that out? Well, if I'm talking about the total weight in pounds, I need to have some flour and some sugar to equal 15 pounds. But then I have the costs with this, and the cost of the flour is going to be 80 cents per pound of flour plus 50 cents per pound of sugar. Maybe S wasn't the very best, the best variable to use here, because the S and the 5 could easily be confused. So I think what I want to do is just change this to X and Y. I chose X for flour simply because flour was listed very first. And so it would be the most reasonable and most mathematically accepted to use flour as the X, sugar is the Y. There you go. That's how we set up our equations. This last one would just tell us how much of, whoops, don't forget the brace, of each ingredient can be bought. Okay? And that's our purpose for it. That's why we write them, and that's how we use them in real life situations. Now, not everybody's going to do this, but this is a quick and efficient way to do this. All right, 15.3. This is going to be, this is the last thing in today's lesson. This goes back similar to like in lesson 14, where we have a lot of systems of equations. And then without solving, you need to identify 3 of them you think would be easy, 3 of them that you think would be difficult, and prepare to explain. My honest thought with this, I think the easiest ones are going to be the ones like this. Letter G, I think, is probably the easiest because Y is equal to just one term and E is equal to just one term. I think that ones that have fractions will probably be the most difficult. Possibly the decimals would also be more difficult. I think D, where it's not in a form that's very familiar to us, where we have slope-intercept form on each of these ones for the most part, but this one is both standard form. So take a thought with it, and you decide which ones you think are easy and difficult. But what your task is going to be is you'll have another Google form to do where you have item B, item D, item F, and item G that you have to solve. And then there's one bonus one. Item C is going to be your bonus, so an extra credit one. I am going to take a couple minutes and just solve item A. Stick around for me for just a minute and let's look at this one. So item A, if you take a look here, I think this one is pretty straightforward. Item A shows that both expressions are equal to the same value of Y. So by that logic, that means that Y is equal to Y. We know that for sure, which means that negative 2 times X plus 6 represents Y, and X minus 3 also represents Y. So those two expressions must be equal to each other. And now I can just go through my process of the properties of equality, and I can find out that 6 is equal to 3 times X minus 3, where I add 3 to both sides. This is 9 is equal to 3 times X, and X must be equal to 3. Once I know that x is equal to 3, I can go back and I substitute back into my equations. Again, one of my strategies is to substitute into the easier equation, or I think quote unquote easier equation, to figure this out, or to figure out what y must be. And in this case, I'm going to suggest that if x is 3, then I'm going to look at this one first. Y equals x minus 3 substitutes to y equals 0. 3 minus 3, and y is 0. And if that's the case, if my ordered pair, what I'm suggesting right now, x is 3 and y is 0, before I conclude that that is the correct answer, I want to double check my other equation. Y equals negative 2 times x plus 6. This ordered pair 3, 0 has to make this equation true, or else it's just not right, and I have the wrong solution. So we'll start here. Negative 2 times positive 3 plus 6 has to be equal to 0. So what I want to look for here and test out, I want to check and challenge that and say negative 6 plus 6 equals 0 and 0 equals 0. I have the right solution. So I know for a fact my one solution here is 3, 0. Okay. Letter E, looking at the decimals, and perhaps we might think, oh my gosh, there's decimals. Yeah, and it's okay, because we have these skills of properties of equality that we can use, where again, we see that both of them are equal to y, and we know y is equal to y. And so we can say 24 hundredths times x is equal to 18 hundredths times x plus 9 tenths. And now with that in mind, what I can do is look at these pieces and start simplifying, subtracting 18 hundredths x. And I get 6 hundredths of x is equal to 9 tenths. And then my last step here is just divide by 6 hundredths on both sides. And now with the understanding that these two values are going to be in decimal form, or it was given in decimal form, I want to go ahead and proceed in decimal form. Oops. And I think that x is supposed to be 15. I want to double check that just to make sure, because I know I did a little mistake there. Oops, 9 tenths divided by 6 hundredths, 15. Cool. Now that I think I have the value of x, now I can go ahead and check everything. Y is equal to 24 hundredths times x, which would mean y is equal to 24 hundredths times 15. And y should be equal to 3 6 tenths. So now I'm getting into the part where I start to believe that I have the right solution. So 3 6 tenths, I believe, is y. And now I can substitute that back into the other equation, or I can simply take the value of x and put it right here and see if y comes out to 3 6 tenths. So I believe that x is 15. When I have y is 18 hundredths of x plus 9 tenths, then I should get 3 6 tenths when I take 18 hundredths times 15 plus 9 tenths. Let's see if that happens. 18 hundredths times 15, and then add 9 tenths, and I do get 3 6 tenths is equal to 3 6 tenths. I know that my x value is 15, my y value is 3 6 tenths. I have the right solution. So one thing I would caution you on, don't automatically assume that there's always one solution. Not every single line is going to intersect. There can be no solution or infinite solutions. Pay attention to the slopes, pay attention to the y-intercepts, pay attention to the things that we talked about before. Things like when you have it in the form ax plus by equals c, a equals a, b equals b, c equals c, infinite solutions or all solutions. A equals A, B equals B, C is not equal to C, then we have none. Different slopes have one solution. Okay, pay attention to those, and what that does is it helps you to visualize it before you get going. So when we look at A, we can look at those two slopes. They're different slopes. There's one solution. B, different slopes, or slope-intercept forms. They have different slopes. One solution. C, 2/3 and -4/3 for a slope. One solution. D, oh, that's in this form right here, and I see that A is equal to A, B is equal to B, C is not equal to C, this is no solution. Be able to prove your work with that. Letter E, different slopes, one solution. F, different slopes, one solution. G, oh, they're trying to trick us here, but I know if I subtract x from this side and this side, I get y equals negative x plus 52, and I see different slopes, one solution. Understanding those pieces to it really helps me to visualize what to expect and to know if I get something that comes out with one solution, but it really should be no solution, just kind of helps guide me and direct where I should be going with that. So we've learned how to solve a lot of different systems equations using algebra that would be difficult to solve by graphing. And the reason that it's difficult to solve by graphing would be instances such as this one, because we get a decimal answer. I'm going to tell you, as you go back in here and you do the Google form, this one right here, since it's given as a fraction to start, your answer needs to be in fraction form. And I'll tell you that intersection is a fractional form. This one we saw the intersection had decimal. This one will have a decimal intersection. And it's possible other ones will as well. So graphing is sometimes not the easiest thing, and it's not the best way to be able to check our work. Algebraically, we'll always come out with that exact value because we can prove it. When we solve for x, this is all just a rundown of the exact same way that we used substitution before to be able to solve, and then substitution to be able to solve for the other unknown variable. So take a look through it. Recognize that it goes on to the next page. We are going to be stepping into ones like these where you can tell that we don't have a variable that's isolated. We are going to learn how to use different strategies for this. One of them is called elimination, but we're going to go ahead and learn how to do that in another lesson. So thanks for working with me today, and be sure to have a great day. Don't forget about the homework and the Google form.